So the other day we briefly talked about what a function is, and now we're going to dive into it a little bit deeper. So a function is a relation between input and outputs. And the most important thing right here is each input has exactly one output. That's the biggest thing. So each input has exactly one output. And when I say inputs and outputs we're talking on our graph would be our x values, and the outputs will be our y values. So inputs x's, outputs y's, right? Because our slope-intercept form, y equals mx plus b, and everything works with the input being x and the output being y. So if I look at these guys down here, each of their inputs or each of their x values has one output or one y. So for example, if I just pretend this is like -2, when x is -2, there's one output on that graph. Same thing, if I come over to let's pretend this is 3. When I go x is 3, there's one output. There's only one y value for that. Same thing with this next graph. Every single input, every single x has one y. Same with the next graph and the next graph. Whereas I look at these next four, now none of these are functions, okay? Because if I think, let's pretend when x is 2, for example. When I plug in 2 for x, I got an output up here and an output down here. So technically, let's just pretend that's like this. So that would be the point 2, 2, and the point 2, -2. So that means the input of 2 has two different outputs. That's why it's not a function. Same thing with this next guy. Let's pretend this is x is 1. You'd have a lot of different outputs when x is 1. You'd have an output here, an output here, an output here, an output here. There's a bunch of different outputs when x is 1. Okay, same with the next one. It's a straight line. So when I input the x value of, whatever this is, about 9 or 9.1 or something, it's got an infinite number of outputs for y. It's got a ton of them. There's 9.0 and 9.1 and 9.2 and all those things. And the same thing with this last one. Over here is good, right? But if I look, here I got 3 different outputs for my x value of, let's pretend that's 2. And there's a way we can test this nice and easy. We call it the vertical line test. So the vertical line test is used to determine whether a relation is a function. So all we do, if all possible vertical lines that are drawn cross the graph once or not at all, it's a function. Okay, so a function if it crosses it once or not at all, a vertical line. A graph does not represent a function, so not a function, use this red, not a function, when it crosses it 2 or more times, okay, when a vertical line crosses it 2 or more times. So if I look at the 2 I got down here, this left one is a function because if I draw a vertical line anywhere, I look at all those vertical lines, how many times did it cross my graph? Once, 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 once. There you go. Any vertical line I would ever draw only crosses it one time. Whereas I go to this next guy, draw a vertical line. Ooh, twice. It crossed it twice. I already know it's not a function. If I keep drawing vertical lines twice, 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 all it has to happen is just once. If one time it crosses the graph twice, that automatically makes it not a function. So if I quickly went back, I looked at the ones that are a function, crosses it once, 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 okay? Same thing here. Even though they're dots, it's still the same thing. I can go through the dot once, once, once. You look at each vertical line individually. It's only crossing the graph one time every time I draw a vertical line. Same thing. Once, once, all that stuff. Whereas all these that are not a function, all right, crossed it twice, not a function. Well, if you look at this one, that one, it crossed it once. Okay, so does that make it a function right there? No, I'm looking at the entire graph. If I draw one right here, oh, now it crossed it a bunch of times. Right here, right here, right here. Okay, so just because it does it if there's one vertical line that crosses more than once, like this green guy, that automatically makes it not a function. Okay, even though this blue guy worked, as long as one vertical line screws it up, then the whole thing is not a function. Looking at the next one's kind of tricky, but yeah, if I draw a vertical line on the vertical line, it crosses it forever. So that's why it's not a function. And here, this one's good, 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 not good, right? Because I crossed it 3 times. So not a function. So you just use that little vertical line test. So let's just look at a couple here. How about this first one? Well, it's a vertical line, so draw a vertical line through the graph. Well, crossed it a bunch of times, not a function. How about this next one? Well, it looks good, right? Because it's crossing the line once, but this graph is of an inequality, right? And aren't all the points like on that line plus above it in that shade, isn't that a solution? So technically that vertical line is crossing all those points that are solutions here. So that would not be a function. That's kind of a trick question. So you got to pay attention. The shade is also a part of the graph. All right, so let's graph some of these guys. So if I plug in -2 for x, that's going to make this -6 plus 4y equals 12. And if I add that 6 over, I would get 4y equals 18. And y would be 4.5. So let's go ahead and graph that. -2, 4.5. -2, 4.5. Somewhere right in there. Plug in 0 for x. So I got 0 plus 4y equals 12. Well, 4 times 3 gives me 12. So y is 3. So at 0, 3. Plug in 0 for y now. So 3x plus 0 equals 12. So 3 times what gives me 12? 3 times 4. So 4, 0. Should be somewhere about right there. Plug in 6 for x. So 3 times 6 is 18. 18 plus 4y equals 12. Subtract the 18 over. And we got 4y equals -6 divided by 4. And y equals -1.5. What do you think? Is this guy going to be a function or not a function? Yeah, this would be a function. And should I draw my line through these points? Yeah, because I got to consider all the points in between -2 and 0 and 0 and 4 and 4 and 6. So I would draw my line in just like that. And yes, this would be a function because for each input, there's exactly one output. Very nice. How about looking at this guy? All right, so let's plug in 0 for y. So 0 squared equals x. Well, 0 squared is 0. So we got 0, 0. And then we got 4 for x. So y squared equals 4. So what squared gives me 4? Well, 2 squared gives me 4. Right? 2 squared would give me 4. Doesn't -2 also give me 4 when I square it? Yeah, -2 squared would also give me 4. So that gives me two things. So I got 4, -2, and 4, 2. So I got both those points. Okay. What about when y is 3 and -3? So I'll plug in 3 for y. So 3 squared equals x, and -3 squared equals x. So we should get 9 and 9. X equals 9 for both those. So I'd have 9, 3, and 9, -3. It's kind of similar to that last one. What about when y is 9? So if I plug in 9, 9 squared would give me 81. Ooh, that's going to be big. I won't be able to fit that on my graph, but 81, 9. Okay, and then 100, what would that be? Well, let's kind of think about what we've been doing. If I plug 100 in for x, then that equals y squared. I should get 10 and -10. So what actually happens here, and we'll learn this in just a few sections, that if I really wanted to solve for y, right now I'm squaring y, right? And whenever we want to get a variable by itself, we do the inverse of what's being done. And what's the inverse of squaring? Well, square rooting. And whatever I do to one side, I do to the other. Because if I square root a square, they cancel each other, and I'm just left with y. But we have to be careful that anytime I square root both sides, I always get plus, minus. Plus and minus the square root of 100. Because that's 10, so I'd have plus or minus 10. So y is actually 10 and -10. So when I have the plus and the minus, that means a positive 10 and a -10. So that's something new that we'll be using here. So 10 and -10. And plus that won't fit, but if I draw my lines, my graphs here, they start curving just a little bit. And this would not be a function, right? Because if I did the vertical line test, right there crosses it twice. Plus if I look, this input of 4 has two outputs of -2. And same thing right here for this 81. When x is 81, it goes to 9. It should also go to what? -9 as well. Okay, so just some things to look at there. So here's some examples of functions, right? I should just check. Does each input have one output? 3 has one output. -14, one output. One output. One output. Good. If I were to make a table and I plug in a number for x, for example 1, I'd get 2 times 1, which is 2. Would I ever get 2 answers for y if I plug in one number for x? No. If I plug in 4 for x, I'm only going to get one answer for y. Right? So each input has one output on a graph. I use my vertical line test. Okay? It has to cross it one time at each vertical line for it to be a function. And it could be in a diagram, right? So 3 has one output of 6. Negative 14 has one output of negative 28, so on and so forth. So that would also be a function. All right, and we defined these the other day, but now we're going to use them more so. So remember, domain is your inputs, and it's typically the x values on a graph. So domain inputs. And I always think domain starts with D, x comes before y, all right? So D and x go together. Range, right? So D comes before the R. So range, R, goes with the y values, your output values. So your x's, domains, inputs all come first, right? Because they all come first alphabetically. D comes before R, I comes before O, X comes before Y. That's how I remember they go together. Domain, inputs, X's, and the range, output, Y's. So what we're going to do, if it's discrete, we're going to list it with curly brackets. If it's continuous, we're going to write it as an inequality, and you'll see that as we go here. So if I look at my first example, this is discrete because we have a bunch of dots. So it says list the domain and range. So I'll put D, and I'll start a curly bracket to list my domains. Well, what are my domains? Remember, those are the x values. So maybe I'll just list all my points here. So this point is negative 2, 0, negative 1, 1, 0, 2, 1, 3, 2, 4, 3, 5. So if I'm going to list my domains, that's my x values. So negative 2, negative 1, 0, 1, 2, and 3. So that's what I list. Negative 2, negative 1, 0, 1, 2, 3. Those are all my x values. So then when I do the range, all I do is I list my y values. So 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So when I list the domains, I just list the x values. When I list the range, I just list all the possible y values. And in this case, it's discrete, so I just list them as their numbers. Whereas when it's continuous, right, so I have lines, like the dots are connected essentially. What is the domain and range? So now my domain, remember, is my x values. So look, the smallest x value I have is negative 5. You know, then when x is negative 4, I'm up here. When x is negative 1, I'm here. When x is 1.5, I'm here. X is 4, I'm here. When x is 4.5, I'm here. X is 5. So it goes from negative 5 to 5, but it doesn't go anywhere outside of that. And then we have to include the negative 5 and the 5. So remember how we wrote our little compound inequalities from a couple chapters ago? We'd start with negative 5 because that's our smallest, and we'd say less than or equal to because we're including negative 5. And we put x because we're looking at our x values. And they're also smaller than or equal to 5. So this states that all my values are bigger than or equal to negative 5 and smaller than or equal to 5. So they're in between. Right? I could plug in any x from negative 5 to 5 and I'll get an output according to this graph. And then I can do the same thing for my range. So now I'm going to list an inequality with my y values. Well, what's the smallest y value I could have? Can I have any negatives? No, this graph does not go in the negatives. It stops right here. So what's that y value? Well, that point is 5, 0. This point is negative 5, 0. So the smallest y value is 0. So I'm going to start at 0, and I'll say less than or equal to y, which is less than or equal to, what's my biggest y value? Well, that top of the part of the circle, or the ellipse that I got here. And that would be what? A y value of 5. So this would go all the way up to 5. Okay. If it would go on forever, I'd only need one inequality. So for example, if I made a green graph right here, and I showed something like this, and I wanted to state the domain and range of that, my domain, well, my x's start at 0, and they go on forever. So they're greater than or equal to 0, right? Because I am including every single x forever. If I look at this arrow on the end of it, it's going to keep going forever in that positive direction. And the same thing if I would list the range. My y's start at 0, and they go on forever vertically because of this arrow right here. So they'd be greater than or equal to 0 right there. Okay, and the more you do, the more you'll get used to that.